Okay, so let us now talk about impedance. So, in signals and in circuit analysis, we want to generally avoid using, well, differential equations because solving differential equations takes too long. So, rather than doing that, we use what's called impedance. Impedance just simply describes to you what is in the system that's affecting maybe what's called ob- affecting obstruction, impeding progress, for example. So resistors are simply pathways that electrons can't easily flow through. Capacitors, we have to kind of use an electric field to kind of move and create a separation of charges. A coil or an inductor, current can't easily flow through it because of Lenz's law, which you will see in EE 3450 or 33 30 3050. Now, with all these, we have some resistance R, some capacitance C, and some inductance L. In talking about connecting them together, such as in the case of RCL circuits, we have something like this: R, C, and L. And then maybe this is some voltage. Doesn't really matter. If we were to find the voltage relationship using KVL, we have maybe V equals to something like this. So we have IR plus L di dt plus 1 over C, the integral of 0 to t of I tau d tau. Now, this then begs the question: how do we solve something like this without prior knowledge in in differential equations, without prior knowledge in Laplace transforms, and without prior knowledge in signal and systems? You don't really have an idea of how you would be able to solve a differential equation like this. So rather than doing that, let us not do that. We convert it to impedance form. And here I'm just going to introduce to you the different impedance formulas to keep in mind. For resistors, the goal for impedance is to basically turn everything into resistances. So now resistors stay the same. Actually, for Z, the impedance Z of R is equal to R. Resistance stays the same. We're trying to compare it to resistors. So capacitors, on the other hand, convert into negative J divided by omega C. Now, for inductors, L, ZL is equal to J omega L. From here, by connecting them together, you're actually able to connecting them together in series. It's almost like you have them like this. Granted, of course, these aren't resistors. Capacitor is not a resistor, and neither is an inductor. But by converting them into impedance under the assumption that we're looking at an alternating signal, later on we'll talk about phasors, and we will talk about how impedance plays a role in AC analysis. But for now, these are the formulas. And by connecting them in a series like this, we can actually form the total impedance, like so. R plus J, and then we have, technically we can move J at the bottom, but it's going to be J omega L minus 1 over omega C, like that. And that's the total impedance in the event that it's connected in series. But the idea is later on in phasor, we're going to scrap solving differential equations and start solving algebraic equations. And this is just the introduction for RCO. Okay, thank you.